structure of the atom. The mystery of the invisible kingdom. Imagine you are a scientist who receives a mysterious invitation. Welcome to Atom City. Your mission is to discover what everything in the universe is made of. Your journey begins. Long ago, people asked a simple question. What is everything made of? A wise scientist named John Dalton believed he had the answer. He said, everything is made of tiny solid particles called atoms. People believed him because no one had ever seen inside an atom. For many years, everyone accepted this idea. But one question remained. Is the atom really indivisible? So scientists began investigating. They entered the mysterious world of atoms. To their surprise, they discovered that atoms were not solid balls after all. Instead, they contained three tiny particles. The first was the electron, a tiny particle carrying a negative charge. It moves around the center of the atom. The second was the proton, a positively charged particle found inside the nucleus. The third was the neutron. It has no charge at all and also stays inside the nucleus. Now Dalton's theory was no longer complete. Atoms could be divided. The mystery had only just begun. A scientist named J.J. Thomson decided to investigate further. He performed a famous experiment called the cathode ray experiment. During the experiment, he discovered tiny negatively charged particles. These particles were called electrons. Now Thomson faced another question. If atoms contain negatively charged electrons, where is the positive charge? He imagined the atom like a watermelon. The positive charge was spread throughout the atom. The electrons were embedded inside it, just like seeds inside a watermelon. This idea became famous as the Plum pudding model. Everything seemed perfect until another scientist arrived. His name was Ernest Rutherford. Rutherford designed a bold experiment. He fired tiny alpha particles at an extremely thin sheet of gold. Everyone expected the particles to pass straight through. Most of them did. Some changed direction, and a very small number bounced straight back. Everyone was shocked. Rutherford realized that something very small, very dense, and positively charged must exist at the center of the atom. He called it the nucleus. Now scientists understood three important facts. Most of the atom is empty space. The nucleus is extremely small, but contains almost all the mass, and electrons move around the nucleus. But another mystery appeared. According to classical physics, a moving charged particle should continuously lose energy. That meant electrons should slowly spiral inward and fall into the nucleus. If that happened, atoms could never exist. Clearly something was missing. Rutherford's model could not explain why atoms are stable. Then a new scientist entered the story, Niels Bohr. Bohr proposed a revolutionary idea. Electrons are allowed to move only in certain fixed circular paths around the nucleus. These paths are called stationary orbits. While an electron remains in one of these orbits, it does not lose energy. Only when an electron jumps from one orbit to another does it absorb or release energy. This simple idea explained why atoms remain stable. It also explained the beautiful spectrum of hydrogen. For the first time, scientists understood why atoms do not collapse. Scientists then noticed something fascinating. Whenever atoms were heated, they emitted beautiful colored light. Every element produced its own unique pattern, almost like a fingerprint. This pattern became known as the atomic spectrum. Hydrogen produced several groups of colored lines. Scientists named them the Lyman series, the Balmer series, the Paschen series, the Brackett series, and the Hund series. Bohr's model explained exactly why these spectral lines appeared. But another puzzle remained. Scientists studying hot objects discovered something strange. Classical physics could not explain how they emitted light. Then Max Planck introduced a revolutionary idea. He said that energy is not emitted continuously. Instead, it comes in tiny packets called quanta. he expressed this idea using a simple equation. Energy equals Planck's constant multiplied by frequency. This single idea marked the beginning of quantum physics. Albert Einstein extended Planck's idea even further. He proposed that light itself behaves like tiny particles. These particles are called photons. When photons strike a metal surface, they can knock electrons out of the metal. This phenomenon is known as the photoelectric effect. Einstein's explanation completely changed our understanding of light. Then another scientist asked an unusual question. His name was Louis de Broglie. He wondered, if light can behave like particles, why can't particles behave like waves? He proposed that every moving particle has a wavelength. Even electrons behave like waves. The microscopic world suddenly became much stranger than anyone had imagined. Soon after, Werner Heisenberg made another remarkable discovery. He showed that nature itself has limits. It is impossible to know both the exact position and the exact momentum of an electron at the same time. This became known as the uncertainty principle. It meant that electrons cannot travel in perfectly fixed circular paths. Bohr's model, although successful, was not the complete picture. Then Erwin Schrödinger introduced a completely new way of thinking. Instead of imagining electrons moving in fixed paths, he treated them as waves. He introduced the idea of orbitals. Orbitals are regions where an electron is most likely to be found. Electrons do not move like planets around the sun. Instead, they exist as probability clouds surrounding the nucleus. This became the modern quantum mechanical model of the atom. Every electron carries its own identity. Scientists describe this identity using 4 quantum numbers. The first quantum number tells us the main energy level. The second tells us the type of subshell. These are called S, P, D, and F. The third tells us the orientation of the orbital, and the fourth tells us the direction in which the electron spins. Together, these 4 quantum numbers uniquely describe every electron in the universe. Orbitals can be imagined as the homes of electrons. Different homes have different shapes. The s orbital is spherical, the p orbital looks like a dumbbell. The d orbital resembles a clover leaf, and the f orbital has an even more complex shape. These are the regions where electrons are most likely to exist. Now imagine that these orbitals are hotel rooms. Electrons are the guests. 3 important rules decide where every electron stays. The first is the Aufbau principle. Electrons always occupy the lowest energy orbitals first. The second is the Pauli exclusion principle. Only 2 electrons can stay in one orbital, and they must have opposite spins. The third is Hund's rule. When several orbitals have the same energy, electrons first occupy them one by one before pairing up, just like students choosing separate seats before sitting together. Scientists also noticed another interesting pattern. Some electronic arrangements are especially stable. Half-filled and completely filled subshells have extra stability. This happens because of symmetry and exchange energy. Nature always prefers balance and stability. Finally, electrons begin filling orbitals one after another. Hydrogen has 1 electron in the 1s orbital. Helium has 2. Lithium begins filling the 2s orbital after completing the first shell. Slowly, every element builds its own unique electronic configuration. This arrangement determines the chemical properties of every element. It explains the periodic table. It explains chemical bonding. It explains reactivity. In fact, it explains almost all of chemistry. At the end of your journey, the king of Atom City smiles and says, "You came searching for the atom. But what you actually discovered was far greater. You discovered why atoms exist, why atoms remain stable, why every element behaves differently, why different elements produce different colors, why light sometimes behaves like a wave and sometimes like a particle, why electrons behave like waves, and why chemistry works exactly the way it does. Everything. comes down to one beautiful idea: the arrangement of electrons around the nucleus. Welcome to the invisible world of the atom.